Welcome to this edition of Spaceworks. I'm Lynn Bondurant. During this show, we'll see pictures not only relating to space, but aeronautics. Stories include dedication of the world's biggest wind tunnels and how students use school buses to simulate space shuttle missions. But first, let's see computer animation from the NASA Jet Propulsion Laboratory in California, which shows a distant moon called Miranda that circles the planet Uranus. Since the days of the Wright brothers, airplane designers have been using wind tunnels to check the effect of wind pressures on the airplane models placed in the tunnels. For our next story, we're going to the NASA Ames Research Center near San Francisco, where the world's biggest wind tunnels were dedicated in December 1987. Modification of the world's largest closed-circuit wind tunnel, the Ames 40 by 80 foot, began in 1980. The tunnel had been used for decades before then to test full-scale aircraft, but engineers wanted to increase its capabilities. Although an accident in 1982 caused damage which delayed the project, the goal of making a new test section more than 2 times as big as the old one was accomplished. And the old 40 by 80 foot section, though smaller, had its speed increased from 230 to 345 miles per hour. Now let's see a videotape prepared for the December 1987 dedication, which gives us more detail, including wind tunnel link-up to computers.
At Ames Research Center, the world's most powerful supercomputing capability is teamed with state-of-the-art wind tunnels to form the first steps along the critical path, from computation to flight. The National Full-Scale Aerodynamics Complex at the Ames Research Center in California is the world's largest wind tunnel. This unique facility provides the United States with the capability of performing ground-based aerodynamic experiments on large-scale and full-scale aerospace vehicles and components. Low-speed aerodynamic research is conducted in related fundamental flow phenomena. Research activities include investigations of the aerodynamic performance and control required for efficient takeoff, climb, and landing for all classes of aircraft, and the acoustic implications related to these flight phases. This extraordinary complex includes the 40 by 80 foot wind tunnel, the new 80 by 120 wind tunnel, and the outdoor aerodynamic research facility. This complex is the crown jewel of an elaborate system of wind tunnels at Ames. The NFAC is committed to contributing to United States aerospace leadership and to developing technology to keep U.S. commercial aircraft in a strong world-class position. Even by the mid-1930s, the wind tunnels of the National Advisory Committee for Aeronautics, NACA, had helped transform the wire and rag biplanes of World War I into metal low-wing monoplanes. Accelerated wartime research in Europe spurred NACA to initiate the construction of a whole new aeronautical laboratory out west in Mountain View, California. On December 20th, 1939, NACA broke ground on their new laboratory facilities 40 miles south of San Francisco at Moffett Field, which is now the Ames Research Center of NASA. The overriding military need of the moment was the testing of new aircraft designs at moderate speeds. In 1941, the mammoth construction task of this wind tunnel began at Ames, and 2.5 years later, in June 1944, the full-scale wind tunnel went into operation. This 40-foot by 80-foot low-speed wind tunnel was an invaluable addition to NACA's array of tunnels, since it was big enough to handle all but the largest bombers and transports with their engines operating. The full-scale tests in the 40 by 80-foot tunnel led to research results that in time actually made great improvements in aircraft design and operations. In the early years, NACA wind tunnel tests provided the Douglas XS-BD-2 dive bomber with a modified wing flap system that lowered landing speeds from 90 to 84 miles per hour. This small gain allowed the use of better, high-performance fighters on our Navy's carriers, thus saving lives and aircraft. In the 50s and 60s, the 40 by 80 wind tunnel contributed significantly to the development of jet aircraft control systems and stability. The 40 by 80-foot wind tunnel covered 8 acres of land. The air circuit was just over a half-mile long and was operated by 6 40-foot diameter fans, each powered by a 6,000 horsepower electric motor, which could maintain airflow at speeds up to 230 miles per hour. Over the years, this tunnel became the primary facility in the country for investigating the flying characteristics of large-scale and full-scale aircraft and components. With the advent of the jet age, the tunnel was used to explore the landing and takeoff characteristics of the new aircraft. These two critical periods of flight are extremely sensitive in terms of lift, drag, and stability. In more recent years, NASA became the focal point for extensive research on powered lift aircraft, rotorcraft, and other vertical takeoff and landing aircraft. In the case of the VTOL aircraft, the tunnel tests explored the critical flight regime where the vehicle makes the transition from powered lift at low forward speeds to wing-borne lift at higher speeds. The 40 by 80 also aided in the study of structural dynamics of advanced helicopter rotors and new VTOL aircraft. In many cases, these studies led to successful modifications for their future design and flight. The 40 by 80 was so successful in testing full-scale aircraft that 35 years after its initial startup, the tunnel power was increased to 135,000 horsepower. Modifications were begun to incorporate a new leg of the tunnel with an 80 by 120-foot section where even large conventional aircraft, rotorcraft, and VTOL, STOL aircraft could be accommodated. Modifications of an existing structure can frequently be more challenging than building a new one. The central area of concern in this instance was replacing the original 6,000 horsepower drive motors with an enlarged horsepower capacity system, all within the original space. By using synchronous motors with controllable pitch fans and variable frequency speed controls, the new drive system was fitted into the existing motor support structure. The new fan's design was more efficient and took advantage of the latest acoustic technology for reduction of noise during tunnel testing. Thus, the new 80 by 120 wind tunnel was born, thereby tripling the test section area of the original 40 by 80-foot tunnel. In 1958, NACA was reorganized by an act of Congress and became known as the National Aeronautics and Space Administration. During the 60s, aeronautical research prospered as never before. Although NASA is widely known for its focus on manned and unmanned spacecraft, the agency has continued to contribute giant strides to aircraft technology. U.S. subsonic jets captured the world commercial market and became indispensable to intercontinental travel. As a result of the research at NASA, developments in the variable sweep wing and the improved airfoils were invaluable to more efficient flight in the atmosphere. Besides these aerospace contributions, NASA's research has provided advancements in aircraft efficiency and safety, which have resulted in millions of dollars in savings to the nation. In the later 60s, supersonic transports and fighters were on the drawing board, and there were a great number of assignments for the wind tunnels in support of spaceflight. The NASA wind tunnel was able to answer those unexpected questions that always arise when testing radically new designs. This pushed the capabilities of NASA's wind tunnel facilities and staff and proved the value of wind tunnels for high-priority programs. The Ames wind tunnels played an important part in the design and development of the space shuttle. The shuttle, being a hybrid spacecraft aircraft of unusual shape, operates under extreme flight conditions, and the wind tunnels were needed to test the complex flow conditions encountered from launch to orbit to landing. Even though these craft operate at high speeds, they all go through the critical low-speed takeoff and landing conditions that can be so uniquely tested in the NFAC. For such reasons, the Space Shuttle was one of the biggest challenges for the whole Ames wind tunnel complex. The wind tunnel work paid off, and the unpowered landing tests confirmed the tunnel test results. NASA's contribution to swept-wing technology aided in the design of a diverse range of swept-wing aircraft. The wind tunnels bore much of the testing load for the supersonic transport in the areas of takeoff and landing, transonic acceleration, stability and control, and inlet performance. In order to continue the research success of the 40 by 80-foot wind tunnel, a major modification to it and construction of the new 80 by 120-foot open circuit leg was undertaken. This resulted in an increase of speed to 350 miles per hour in the 40 by 80-foot test section, which is an important increase in research capability. Because of its size and the speed of 115 miles per hour in the 80 by 120, it will be possible to investigate full-scale rotor systems and V-stall aircraft at very low forward flight speeds in a ground-based facility with minimal wind tunnel wall effects. Its size even permits the evaluation of actual aircraft as large as a Boeing 737 jet transport. In addition to the tunnels, the outdoor aerodynamic research facility is used to check out and test aircraft and models in a static environment before they are installed in the NFAC wind tunnels. The facility is an open-air test area designed to test models and instrumentation and collect baseline data. This facility includes a model mounting pad, control room, and other support equipment for remote model or aircraft operation. The Ames 40 by 80-foot wind tunnel has seen over 550 tests and hundreds of different aircraft and models in its test section of virtually every major airframe design. All three areas of the aerodynamics complex have been updated and equipped for the future research that will bring us all into a new technological age. The combination of dedicated people and machines working together from computation to flight since the Wright brothers and their successors will continue on into the space age. Undoubtedly, aerospace vehicles not even yet conceived will fly in this NASA wind tunnel before they embark on their future aviation destiny in our atmosphere or perhaps to the planets beyond. The NFAC wind tunnels have carried the burden of technical advances in aeronautics as well as in space. The years of technical successes result from a truly innovative direction, spearheaded by an extremely technically competent staff, which continues to have the expertise in design excellence and extreme research versatility. Several hundred people, technicians, engineers, designers, model fabricators, mechanics, and their support personnel are required to run wind tunnel tests. This carefully assembled team knows how to use the capabilities of the wind tunnel and use it wisely. Our world is shrinking, and the technological advances inspired by our research here at the National Full-Scale Aerodynamics Complex will promote safer, faster, and more efficient means of travel, and thereby build closer communications, contribute to international understanding, and perhaps world peace through technological advances. From the biplanes of World War I and pioneering rocketry, aerospace technology has progressed to supersonic transport spanning the globe, space probes to the planets, and manned landings on the moon. Winged aerospace vehicles may someday routinely return from orbit to a precision landing here on Earth. Because of this, our facilities and the dedication of our staff promise a future generation of flight that truly challenges the imagination.
Now let's go back to 1979 to see aircraft spin tests at NASA's Wallops Flight Facility in Virginia.
For men like Wayne Lee, Bill Mims, and the rest of the ground crew, it's a job they've done many times in the past. Even so, it's a job they don't rush to finish. Above all, what they do is thorough. The data that will be gathered in today's test flight and safety of the man who will fly the plane are dependent on how well they prepare the plane and its instrumentation for flight. The place is NASA's Wallops Island, Virginia. The plane the ground crew has been working on since 5:30 a.m. is a typical general aviation light aircraft. And this is the man who will fly it, 50-year-old engineering research pilot Jim Patton. When Jim Patton takes the plane up for a spin, that's exactly what he'll be doing, making the plane spin on purpose. The research is being done because about 30% of all general aviation fatalities can be traced to stall spin problems. Repeatedly, Patton noses the aircraft skyward till the small plane stalls. It then pitches over, and the spins begin.
2, 3, 4. Seems to be staying fairly steep. 5, 6. Stable. 7. Recovering, and it's responding slowly.
A typical flight lasts about an hour and a half.
Okay, recovered. There's 1. Nose wheels a little bit.
Occasionally, when he can't recover from a spin, a parachute mounted in the tail is popped to stabilize the spinning plane. Much of the data that may one day help researchers find better ways to design stall-proof aircraft returns to this telemetry station on the ground. Here, Paul Stow and his team of engineers monitor and record results of the day's spins. Research pilot Jim Patton pointed out some of the many modifications that have been tested on the plane.
This aft fuselage strake, the so-called soda straws under the edges of the fuselage, and the fairing back here, which acts as a ventral, were all sized and located on the airplane in the spin tunnel on models. And we investigate these singly and in combination in full-scale flight.
The full-scale testing is only one part of the overall effort. At the Langley Research Center, engineers test models in a spin tunnel and several other wind tunnel facilities there. On an unused runway in West Point, Virginia, south of Richmond, another group of Langley engineers and technicians fly radio-controlled models of the same general aviation plane. Results of these tests are correlated with results from both the spin tunnel studies and the full-scale flight tests. Stall spin research, an intensive program aimed at improving stall and spin characteristics of both presently flying aircraft and for planes designed in the future.
4, pretty stabilized, still spinning up.
Our final story comes from here at the NASA Lewis Research Center in Cleveland. In April 1987, our Educational Services Office worked with some of the Cleveland area schools to create a special education event, a simulated shuttle mission. School children pretend they are astronauts. The youngsters learn through their play during simulated space shuttle missions. 9 elementary and 2 high schools are involved in this space shuttle simulation on April 8, 1987. Besides science and math, students use art, music, dance, and many other subject areas to carry out the project. More than 5,000 students participate. During the project, students learned many details about the U.S. space program. students are preparing for early morning launches from the participating schools. Students suit up for launch. Experiments and cargo are loaded. Volunteers help to convert ordinary school buses to shuttles. Students train for upcoming missions. It's April 8, 1987 in Cleveland, Launch Day, a day when NASA Lewis Research Center is part of a simulated shuttle program with the 9 area schools and student astronauts. The students design uniforms and crew patches, study launch and landing techniques, and plan experiments.
Now we're going to see another experiment by John Bowman. John, what's the problem of this experiment?
The problem is, will the movement of the shuttle affect the absorbent rate of colored water?
And what's the hypothesis?
I think the color of the water is the color that celery will turn.
What equipment or materials are you using?
Drinking glass, water, celery stalk, red food coloring, and a clock.
They establish mission control rooms at their space centers and prepare flight plans for their eventual trip through the galaxy, where they are to land and explore alien planets. The astronauts use onboard computers and two-way radios to communicate with other shuttle crews and mission control rooms.
Mission Control, this is Victory 2 calling.
This is Mission Control. Go ahead.
Tell them what you're doing. Tell them you're being photographed.
I'm being photographed here on Victory 2.
The night before liftoff, each crew enjoys a sleepover, and a pre-flight breakfast is prepared too. And then, blast off.
7, 6, 5, 4, 3, 2, 1. Liftoff. All right, and we have liftoff. Perfect.
During their travels, there is a rendezvous at the NASA Lewis Research Center to acquaint the aliens with one another. That's it for this edition of Spaceworks. This is Lynn Bondurant saying goodbye from the NASA Lewis Research Center in Cleveland.